To recap, we designed a 25-gram robot with the ability to jump 1.5 meters using 2 torsional springs, a 4-stage gearbox, and a snail cam releasing mechanism. Since the last presentation, our design has undergone a few changes. Firstly, we changed the design of our main leg, replacing the aluminium section with carbon fibre rods connected by plastic joints. This allows the main leg to withstand the stresses during takeoff whilst keeping the weight low. We also realised the carbon fibre rods connecting the side plates would experience high bending moments due to the stresses generated by the torsional springs. To alleviate this problem, we added 2 extra mounting plates and allowed the rods to run through them. Here is the final prototype we have made. The main body, upper main leg, worm gear and leg joints were built using a 3D printer. The parts were printed using Endure plastic, which offers high toughness and has a good surface finish, which reduces drag. Furthermore, its high impact resistance is also good for the push-fit closures used to fit the parts together. With the help of an Ashby chart, we chose carbon fibre rods for the feet and legs due to its high strength relative to its weight. During landing and takeoff, the legs will experience large forces, so carbon fibre is ideal. We purchased a pair of torsional springs with 2 Newton meters of torque per revolution each to provide sufficient propulsion for our robot. For our prototype, we used the same motor presented in our design presentation, and a lithium polymer battery was purchased to power it. The spur gears used in the 4-stage gearbox are made from plastic and were also purchased from an external supplier. The snail cam was printed from acrylic using a laser cutter, as greater strength was needed for this component. For the remote control aspect of our design, we soldered together a crude IR sensor circuit using an infrared phototransistor. This image shows the transformation of one of the main body panels. In the first design, we noticed the push-fit holes were too tight and the parts would not fit together properly. After changing this, we realised the spring shaft was too tight, as we hadn't accounted for the contraction of the diameter of the spring when it's compressed. In our third body panel prototype, small adjustments were made to optimise the smooth running of the gears. The fourth version included significant weight reduction. Here is a video of our first prototype test. As you will be able to see, our robot's mechanism successfully charges and releases the torsional spring. However, due to unforeseen problems with the lithium polymer battery we had purchased, we were forced to carry out the test using a much larger lithium phone battery to power the robot. Hence, unfortunately, the robot was not physically able to jump. In spite of this setback, we are confident that we are on target to produce a successfully operating jumping robot. Our next steps are to resolve our electronic issues with a smaller circuit board and a functioning lithium polymer battery. Thank you for watching.